All right, I have a relatively short video for you to introduce you to Leaf Energy Balance. So relatively short, I've got 12 slides, so hopefully this won't take too long. Okay, so what is a Leaf Energy Balance? So it's just kind of capturing and quantifying how much energy comes into the leaf and how much leaves the leaf. And by kind of like understanding all the energy inputs and energy outputs, we can do a better job of understanding the microenvironment plants are growing in. And really what we're thinking about with leaf energy balance as it relates to leaf microenvironment is like how hot is that leaf relative to air temperature, and what's the rate of water loss from that leaf. And so those are the two big factors we can get from it. And it turns out, we'll read some papers next week related to this, but it turns out that, characteristics of leaf size and like how many hairs are on the leaf and things like that can really impact the leaf temperature. And that can affect where a plant can and can't grow. So kind of what we're talking about, I don't know, it's one of the cooler concepts, I think, in plant physiology, and understanding how leaf shape and size impact where big plant can grow or not grow. So let's get into it. Some of these figures are directly from the book because I think this section is pretty good in the book. So this is the overall equation to figure out energy balance of a leaf. And so I'll walk you through the equation real quick, and then we'll talk about each of these components. So we have the net amount of short wave radiation that's entering the leaf. So that's going to be how much is entering the leaf subtracted by how much is leaving the leaf to give us the net input of short wave radiation. We've got long wave radiation, again, the net input into the leaf. C is the sensible heat loss. They call it convective heat loss in the book, but more often, I think in the literature and talking with people, we refer to this as sensible heat loss, and that's the heat loss due to convective loss of heat from the leaf. And it's sensible, like you can actually feel the temperature, right? That's why it's called sensible heat loss, which is the kind of different from this term here. So this is lambda times E is all a single term. That's latent heat loss. That's the heat loss due to evaporative cooling or evaporative loss of water from a leaf. And then M is metabolism. And so if we are able to capture all of these components of the leaf energy balance, and the leaf temperature is remaining constant, then all of these values should add up to 0. If they don't add up to 0, that means the leaf is either warming up or cooling down. So that's the main take-home message here. All right, so let's just talk about each individual component fairly quickly. This, again, is the figure from the book, kind of representing or visually representing the leaf energy balance. And then I've written a little text over on each side that I won't read, but basically what I'm saying should be over here. So this these pink arrows represent the short wave in to a leaf, and then these are the short wave leaving a leaf. So the leaf is absorbing quite a bit of the short wave radiation. There's a little bit that's being reflected off the leaf, which is represented by this pink arrow. Some of it actually passes all the way through the leaf, which is this transmitted part. And then remember, some of it is fluoresced. When we measured fluorescence, we were measuring some of that shortwave radiation that was re-emitted at a slightly longer wavelength, but still within the range of shortwave radiation. And so those are the major factors of shortwave radiation. But when we're calculating shortwave, the net shortwave radiation entering a leaf, it's during the daytime, it's almost all going into the leaf, and very little of it is leaving the leaf or being reflected from the leaf. So it's mostly inputs. But of course at night, so the sun is the primary source of shortwave radiation. So at night, the plant's really not receiving that much shortwave radiation. It's mostly long wave radiation at night. Okay, let's talk about long wave radiation. So these are represented by the gray bars here. So we've got long wave radiation coming into the leaf, and then of course long wave radiation leaving, and that can often be quite similar. The amount of long wave radiation coming in can be about the same as long wave going out. Sometimes it's more going out than coming in, and so let's talk about why that would be. So any object that's has a temperature above absolute freezing. So absolute freezing would be 0 degrees Kelvin, right? So and we've never created 0 degrees Kelvin, as far as I know. We've gotten close, but people can't get anything that cold. So it's more of a theoretical thing. So anything above that is going to be emitting long wave radiation. And so how much long wave radiation it emits is simply based on the temperature. And I don't want you to remember this equation, but I just thought I would show it to you so you're aware. So this equation here is the amount of long wave radiation being emitted by an object. The first term here, the epsilon, is the emissivity of an object. Now, when we're talking about radiation, there's this, again, theoretical object called a black box. And a black box absorbs all long wave radiation and perfectly emits long wave radiation. And nothing that we've created is a perfect black box. A perfect black box would emit 100% of the radiation based on its temperature. But not every object does that. And it depends on the texture and the structure of the material. But most objects get pretty close to 1. So leaves tend to be between 0.94 and 0.99. So that just means they're emitting 94 to 99% of their potential long wave radiation. So that goes into the equation. Sigma here is just the Stefan-Boltzmann's constant, and I won't go into that, but that's a constant value that never changes. And so the main thing that's affecting long wave radiation of a leaf is just its temperature to the 4th power. And that would give you how much long wave radiation is occurring from a leaf. So you can kind of start to think about like the net long wave radiation entering a leaf based on temperature. So if the ground is warmer than the leaf, then it's going to be emitting more long wave radiation to the leaf than the leaf is emitting toward the ground. And if the atmosphere is warmer than the leaf, then it's all of the molecules in the atmosphere are emitting long wave radiation, and so it would be emitting more than the leaf. But as the leaf gets warmer than the ground or the atmosphere, then the net long wave radiation is actually going to be out of the leaf because it's emitting more away from the leaf than it's absorbing from those objects. Okay, the next one I want to talk about is metabolism. And so this I think is pretty obvious now. Oh shoot, I forgot to change this slide. Let me change it real quick. Hold on, you're going to have to watch this. It's not M's and C's, it's just M. Okay, so most or a large part of the shortwave radiation entering a leaf is used to drive photosynthesis, right? And so that's just what the M represents. So how much of that input of radiation is driving photosynthetic processes. And remember, if it's not driving photosynthetic processes and it's not being re-emitted through fluorescence, then it's actually creating heat, which then, we're going to come to this in a second, and that's what the C represents. It represents convective heat loss or gain by the leaf. And so as the leaf, if it's not using, again, all that shortwave radiation for photosynthesis and the leaf is heating up, then it's going to start losing heat through these convective processes. So that's M, is metabolism. Now, before we get to the last two, we have two more things in the model, or the boundary layer, the leaf energy budget equation. We've got convective heat loss, and we've got, which is sensible heat loss, and we've got latent heat loss. Before we get there, I want to talk about boundary layer, because this really controls the rate of sensible heat loss and latent heat loss from a leaf. So the boundary layer is a layer of what people refer to as still air next to the leaf. And the way I describe this in my undergrad class, just to help, I think, contrast the different ways molecules are moving, but it's a layer of unmoving air molecules next to the leaf surface, or really any unmoving object. So I think in some ways a better way to visualize this is thinking about rivers, because air and water, they're both fluids, right? So they adhere to the same laws. And so if you look in a river, next to like a rock or the bank of the river, the water's moving really slowly. And it's because that unmoving object is creating or providing resistance against the movement of the fluid. And so as you get closer and closer to that unmoving object, like the rock or bank, that the water moves slower and slower. And even though we can't see it, at some point, water molecules right adjacent to that rock, for example, they aren't moving at all because there's so much resistance being applied to that water. And so that happens with air as it's moving over a leaf as well. And so what we get is we get this layer next to the leaf where those air molecules, they're moving a little bit, but at very different patterns and rates than the air of kind of what we call the bulk atmosphere. So most of the air, like if we're imagining a cool breeze or a breeze blowing across the leaf, that breeze would be the bulk air. But right next to the leaf, there's going to be these air molecules that are moving very different, at a different rate mainly than that bulk air. And that's our boundary layer. So this dotted line is representing the boundary layer thickness. And you can see we've got the arrows are supposed to be showing you that the air movement inside the boundary layer is very different than outside the boundary layer. All right. So we're going to come back to this figure in just a second. The important thing right now for us to remember is that this boundary layer, because these air molecules are moving very differently, this creates a resistance to the movement of things through the boundary layer. So if the leaf is warmer than air and the air is moving heat away from the leaf through those convective processes, a thick boundary layer is going to slow the rate of heat loss because it's such a thick area, it would slow it down, whereas a thin boundary layer would allow that heat to move out pretty fast. Same thing happens with CO2 in water vapor, right? So if water is leaving a leaf, it's going to be able to move away from the leaf faster in this thin boundary layer than a thick boundary layer. And same with CO2 coming into the leaf. It's going to move faster through a thin boundary layer than a thick boundary layer, okay? And this just represents the different resistances for heat, water vapor, and CO2. We've talked about them most for CO2, but just point out a couple things here. That heat loss is only going to be affected by the boundary layer, or the boundary layer resistance or conductance. Water vapor is affected by the boundary layer, but also stomatal conductance. And then CO2 is affected by boundary layer, stomatal conductance, and mesophyll conductance. So they're all governed by slightly different or different numbers of resistances. All right, just one last thing on boundary layer that's going to be important for us is that there are three factors that impact how thick a boundary layer is adjacent to a leaf. So this boundary layer thickness is very dynamic. It's changing all the time. And so it's changing in large part, the dynamic nature of the boundary layer is driven by wind speed. So down here, I have a statement about boundary layer thickness, and then these are the three factors that impact boundary layer thickness. Wind speed is one of them, so faster wind speeds result in thinner boundary layers. Leaf size, so a bigger leaf leads to a thicker boundary layer, and we can kind of see this in the diagram here. So let's call this a fairly large leaf, and you can see that as the wind first hits the leaf, the boundary layer is really thin, but the longer that wind passes across the leaf, the more the resistance of the leaf causes a change in the movement of these molecules, and that boundary layer gets thicker and thicker. So if we were to take an average, for this leaf, maybe boundary layer would be somewhere about where I'm moving my icon here. Can't think of the real word right now. Let's imagine, though, that we had a much smaller leaf that was only yay big. Let's see if my drawing is working. I don't think it's plugged in. Oh, yeah. Okay, say that is our boundary layer. Or sorry, this is a smaller leaf. And so if the boundary layer would behave the same way on this small leaf, but because it's so small, the boundary layer never gets very thick. So an average boundary layer thickness on the small leaf would be much thinner than the thick leaf. And then the last thing that affects boundary layer thickness is surface roughness. So in this picture, this leaf, looks really smooth. And so we get this, boundary layer thickness pattern for this smooth leaf. If this leaf had a bunch of hairs on it, that would cause the molecules, it would stir up the molecules faster and cause them to change the rate of movement. And so what that does is effectively creates a much thicker boundary layer if you've got a bunch of hairs on this leaf. And so that can be really important in controlling boundary layer thickness. We'll read some papers, or at least a paper, that talks about hairs and boundary layer and leaf energy balance in the coming week or so. Okay, now we can talk better about latent energy fluxes or losses from a leaf and sensible heat losses. So latent heat or latent energy loss from a leaf, it's called both things. That's why I'm kind of going back and forth. But try to remember latent energy. This is a symbol of latent energy, and all that it is its transpiration rate multiplied by the heat of vaporization of water. And that puts the units from moles of water vapor per meter squared per second to watts per meter squared. So it puts it in energy units essentially. So that's why it's a little different than transpiration. Just reminding us of how we kind of quantify and model transpiration. It's the conductance to water vapor, and remember that's going to be both stomatal conductance and boundary layer conductance, and that's multiplied by VPD. Remember that's the difference between water vapor pressure or vapor pressure inside the leaf relative to vapor pressure outside the leaf. And again, just to get that in units of energy, we multiply the conductance to water vapor by the latent heat of vaporization, and that gives us that in latent energy. So latent energy is where the boundary layer conductance becomes really important. And then in sensible heat flux, remember the only thing governing the rate of movement of heat from the leaf is the boundary layer conductance. And then, of course, the difference in air temperature from leaf to air. So this is our equation for sensible heat loss. So it's the difference between the temperature of the air and the leaf, and then multiplied by the conductance of the air to heat. That's why the subscript is AH. And remember, this is governed by boundary layer thickness. So that's why boundary layer becomes so important. It's in both of those equations for latent heat or latent energy flux and sensible heat flux. Okay, that's it. That's all I've got. That's pretty fast, right? I don't even know how much time it was because my clock's not up. But yeah, that's the introduction to leaf energy balance.